All right, zero fluff. We are jumping straight into the absolute biggest mistake students make when tackling the defects and impurities syllabus in Cambridge AS and A-Level Physics 9702. So many learners walk into this exam feeling totally confident, only to just bleed marks because they fall into one very specific trap. So today we're going to dismantle that trap entirely.
Okay, let's dive into this massive misconception. Most learners assume that a flawless, perfect crystal structure is exactly what engineers want. I mean, you picture a perfectly ordered lattice, right? It makes sense, but physics actually shows us otherwise. In fact, if we only ever worked with completely perfect crystals, modern technology as we know it would literally not exist.
And look at this. This brilliantly illustrates the cost of ordinary revision. This is brutal feedback directly from the examiner. You can memorize all the vocabulary, you can drop the word doping into your paragraph, but if you don't know how to frame the actual physical consequence of that action, you will lose the marks instantly. The examiner doesn't just want the buzzword, they want the actual physics.
So, to make sure you secure top marks and avoid that dreaded examiner's red pen, here is our roadmap for this explainer. We'll start with the cold open mistake, map out the anatomy of an imperfection, build our core framework, run a 2-student answer duel, dissect the examiner's red pen, and wrap up with your exam rescue route.
Let's kick things off with Section 1, Misjudging Imperfection. Here is the crucial point. This chapter is incredibly powerful when you learn it through reversal. Imperfection isn't always an accident. While, yes, an unwanted defect can definitely weaken a solid and reduce its performance, controlled imperfection is actually a deliberate design strategy. It's a highly controlled tool used constantly in modern physics to create specific, desired behaviors in materials. When you shift your mindset from thinking defect equals bad to defect equals highly controlled tool, you unlock the real conceptual target of this syllabus. All right, moving into Section 2, before we get to the high-level exam strategy, we need to map out the anatomy of these imperfections. The physical picture always starts with departures from ideal crystalline order. Your primary culprits here are vacancies, interstitial atoms, dislocations, foreign impurities, and deliberate doping. And you absolutely must strictly classify these departures. Why? Because blending them all together in an exam answer is a guaranteed way to lose points. A vacancy is not a dislocation. A random foreign impurity is totally different from deliberate doping. Blurring these lines will cost you dearly. Now, in just a moment, I'm going to show you the exact examiner clue that transforms a weak 1-mark answer into a full 3-mark response. But first, you need the framework that makes that clue completely obvious. Because trust me, once you see it, you'll never answer a material property question the same way again. Which brings us right to Section 3, our core framework of cause and effect. This right here is your top band blueprint. Step 1, identify the specific defect type. That's your concept. Step 2, identify what changes physically, your evidence. Step 3, apply the scientific reasoning. Ask yourself, how does this alter motion, or bonding, or strength? And finally, Step 4, use that specific examiner wording to connect the microscopic change to a macroscopic, practical consequence. You've got to link the microscopic cause directly to the macroscopic effect. Let's actually look at Step 1 of our framework in action. Keeping this precise definition of a point defect in your pocket ensures you hit the ground running. By accurately stating that it's a highly localized departure from ideal crystalline order, like a vacancy or a substituted foreign atom, you immediately signal to the examiner that you know exactly what you're talking about. Your classification is secure. Let's test this out in Section 4 with a 2-student answer duel, focusing on doping in semiconductors. Okay, pause and predict time. Look closely at these 2 answers. Both students are responding to a question asking to describe why doping is useful in semiconductor technology. Try to spot the error on the left side before I reveal why the examiner handed the right side full marks. I mean, the left side sounds okay at first glance, right? It makes the silicon better, but let's see what our framework reveals. And this brilliantly illustrates our framework in action. Student A dropped the buzzword impurities, but completely failed to mention the physical effect. Saying something is better for electronics means absolutely nothing in physics. Student B, however, understood that doping is a deliberate design strategy. They clearly identified the physical change, which is altering the carrier balance, and then they linked it directly to a practical consequence, producing P-type or N-type behavior for silicon devices. That right there is exactly how you secure the marks. As you can see on this table, this cause and effect relationship applies across the entire syllabus. In semiconductors, deliberate doping changes the carrier balance. In metals and metallurgy, controlling defects and greens balances the material's strength and toughness. And over in high-performance optical or magnetic materials, introducing foreign impurities alters color, response, or transport properties. Every single microscopic modification has a measurable, practical physical outcome.
Let's escalate the stakes in Section 5 and look at exactly what triggers the examiner's red pen.
Here it is, explicitly derived from Cambridge Examiner reports. The absolute most common weakness is mentioning an impurity or the doping process without stating what physical effect it actually has on the material. If you write a beautifully detailed paragraph about how a dislocation forms, but you totally fail to mention how it alters the bonding or structural strength of the metal, you are leaving your grade boundary entirely up to chance. You've basically only given them half the story.
Okay, let's wrap this up with Section 6, your exam rescue route.
Think of this as your survival toolkit for when an exam question throws you a major curveball. When you're revising this chapter, just repeat these 4 anchor prompts. 1. Recall the precise definition. 2. State the microscopic cause. 3. Explain the macroscopic physical consequence. And 4. Give a real application. If you can mentally speak through these 4 prompts in that exact order, you can reconstruct a perfect answer for literally any material weakness or electronic usefulness question they throw at you.
So this explainer gives you the conceptual framework to master defects and impurities. But I want to leave you with a provocative thought. You now know how to describe or explain an impurity perfectly. But what happens when the Cambridge exam command word suddenly shifts to evaluate, or demands that you analyze a complex data table regarding these exact defects? Guaranteeing those top bands requires mastering how different command words demand entirely different answer structures. And that is exactly the vital skill we'll be decoding in our next explainer. Keep this framework close, and I'll catch you next time.